In this video, I will be giving an introduction to the adiabatic processes and showing how to calculate the adiabatic rates using a sample problem. So, what is an adiabatic process? An adiabatic process is when air is forced to cool or warm based on a change in pressure due to vertical movement. When air is forced up, it cools. As air rises, the pressure drops. As a result, air expands, which then cools that air, leading to drops in temperature. When air is forced down, it warms. As air is descending, external pressure increases. The air is then compressed and it warms, leading to an increase in temperature. Remember, the only thing that changes is the altitude of the air. That's what makes adiabatic processes special. Because the only factor that changes is altitude, we can determine standard rates at which the temperature changes. There are two rates. They are dry adiabatic rate and saturated adiabatic rate. The dry adiabatic rate, or DAR for short, is 10 degrees Celsius per 1,000 meters in the metric system. If we wanted to put this in terms of English, it would be 5.5 degrees Fahrenheit per 1,000 feet. The saturated adiabatic rate, or SAR for short, is 6 degrees Celsius per 1,000 meters in the metric system, or 3.3 degrees Fahrenheit per 1,000 feet in the English system. The DAR is used when the air is unsaturated or hasn't reached the dew point temperature yet, or 100% relative humidity. The SAR is used when the dew point temperature has been reached and is past 100% relative humidity. Remember to use the correct degree system, Celsius or Fahrenheit, depending on the units in the problem. There are a few other terms to note when discussing adiabatic processes. First is the lifting condensation level, which is also known as the LCL. This is the altitude at which the dew point temperature has been reached. This marks the start of precipitation where 100% relative humidity is reached. Windward is the side of the mountain where the air is rising, cooling, and precipitating. Leeward is the side of the mountain where air is descending and warming. No precipitation occurs here. Last is the rain shadow effect. This means the leeward side of a mountain tends to be drier and warmer than the windward side. Calculating temperatures using the dry and saturated adiabatic rates is similar to calculating temperatures with the average lapse rate from lab 6. Step 1 is to find the elevation or altitude difference between the current location and that which you want to know the temperature of. This is done by subtracting the minimum from the maximum, or lower number from the higher number. Step 2 is to multiply the difference found in step 1 by the DAR or SAR. Remember, if the temperature is at or below the dew point temperature, use the SAR, and if the temperature is above the dew point temperature, use the DAR. Step 3 is to add or subtract the temperature change amount from or to the temperature given. Remember, if you're warming or descending in altitude, add the temperatures. If you're cooling or rising in altitude, subtract from the temperature given. Here is an example problem involving adiabatic rates. If the dew point temperature is 20 degrees Celsius and the temperature at the bottom of the windward side of the hill is 40 degrees Celsius, what is the temperature at the bottom of the leeward side of the hill? Let's take a closer look at the diagram to determine this. Here I've blown up the diagram and added the DAR, SAR, and dew point temperature to the top left corner of the slide. Essentially, we're given the temperature at point A on the left and told to find the temperature at point B on the right. Looking at the hill, we see it increases in altitude from 0 meters to 4,000 meters at 1,000 meter intervals. Let's fill in our starting temperature. Our starting point is 40 degrees Celsius. Since we don't know where our dew point temperature or if our dew point temperature gets reached, we need to change the temperature every 1,000 meters at the DAR first. If we multiply 1,000 meters by our DAR, we get 10 degrees Celsius. Since we're increasing in altitude and cooling, we subtract that amount by our current temperature. This means 40 minus 10 equals 30 degrees Celsius. Since we have not reached the dew point temperature, we continue using the DAR as we increase in altitude. Because we know the change is 10 degrees Celsius for every 1,000 meters, we can just change the temperature by 10 degrees every increase. So, 30 degrees Celsius minus 10 degrees Celsius equals 20 degrees Celsius. Now that we've reached 20 degrees Celsius, our dew point temperature, we need to change to the SAR, or saturated adiabatic rate. Using that rate, we can continue upward in altitude. To find the next marker, we again multiply 1,000 meters by the SAR. This gives us 6 degrees Celsius. Since we're increasing altitude and cooling adiabatically, we subtract it from the previous temperature. This means our temperature at 3,000 meters is 20 minus 6, which equals 14 degrees Celsius. We have one more marker to go before we descend in altitude. Since we're still below the dew point temperature, we continue to use the SAR. When we subtract another 6 degrees from our current temperature, we get 8 degrees Celsius as our temperature at the top of the hill. We're halfway there. Now we descend, which means our temperature will increase. We use the DAR because there is no more moisture. Since we will be going to 0 meters and know that the adiabatic rate will stay the same the entire way down, we can do the entire distance in one calculation. From the top of the hill to the bottom is 4,000 meters. When we multiply this by the DAR, we end up with the amount 4,000 times 10 degrees Celsius divided by 1,000. When we calculate that, we come out with 40 degrees Celsius. The last step is to add that amount to our starting temperature, which is 8 degrees Celsius. This gives us a total of 48 degrees Celsius. The temperature at the bottom of the hill on the leeward side, or at point B, is 48 degrees Celsius. To better define what I did, I've labeled the places at which rates are used. We first use the DAR until we reach the dew point temperature, also known as the LCL, or lifting condensation level. Past that, we switched to the SAR until we reached the summit. When we descended on the other side, we used the DAR the whole way down. That's the end of this video. If you have any questions, let me know. Bye.